little derivation to help you see why the Gibbs free energy is equal to the enthalpy plus the temperature times the change in entropy. We are not going to do any specific problems. I just wanted to present this to you so you don't, sometimes people feel like that Gibbs free energy just comes out of nowhere. So here we go. Our change in the universe is equal to the change of entropy of the system plus the change in entropy of the surroundings. We said that the change in entropy for the universe is greater than 0 for a spontaneous process. So again, we can have a decrease in entropy for a particular chemical reaction. What has to happen overall? Overall, the change in entropy of the universe has to be greater than 0. All right, now, first of all, we're going to calculate the entropy created by matter dispersal. That's going to be considered to be the change in entropy of the system. The change in entropy of the system is something we can measure. We're going to next calculate the entropy created by the energy dispersed. Okay, so what happens in the surroundings? The energy is dispersed into the surroundings. Okay, so the entropy created by matter dispersal is considered to be the change in entropy of the system. So why is that? Because we're going to look at the system, we're going to see what happens between the reactants and the products, okay? And so that's what happens to the entropy in the system. How are we going to look at the entropy in the surroundings? We're going to look, the system is either taking in or giving out energy. So we're going to look at the entropy created by energy dispersal, and we're going to consider that to be the the change in entropy of the surroundings. And we're going to look more specifically at dissolving ammonium nitrate in water. This is what we call, we said this before, an entropy-driven process. Now, what do we mean by that? When we're talking about that, well, what's causing it to be spontaneous? It's not an exothermic reaction, it's an endothermic reaction. And so it's that dispersal of matter that's causing it to occur spontaneously. And so that's considered to be an entropy-driven process. The change in universe is the change of entropy of the system plus the change in entropy of the surroundings. So what's happening in the surroundings? The surroundings are actually sending energy into the system, okay? And so that's a decrease in entropy. But what's overall happening when the ammonium nitrate dissolves, we're getting more particles. And so this solid, okay, is able to still increase the overall entropy of the universe, okay, by this increase in entropy within the system, okay? So all we're looking for is an overall increase in the entropy of the universe, okay? All right. All right, we're going to take a look at another set. If we were to look in the back in the appendix, we could figure out that the change in entropy for the system is negative 326.9 joules per Kelvin. Now, we're going to try to change, because it's going to be very, very difficult for us. We could, in my previous ammonium nitrate example, I could relate it in some general terms, okay? Energy is concentrated in the surroundings, but we get these aqueous ions, and so the system still is enough dispersal that the overall dispersal in the universe is positive. But trying to figure out that entropy change in the surroundings is going to be very, very tricky to figure out on anything other than a general point of view. So what we're going to do is we're going to change it into something that we can measure that is within the system. Okay? So our change in entropy of these surroundings could be considered to be the Q of the surroundings divided by the temperature. Now, why is that? I said that the surroundings were affected by how energy is dispersed, right? If we're talking about energy, we're talking about Q. And so it's the Q of the surroundings, right? Now, does anybody remember when you did calorimetry, what did you say? You said that the Q of the system is equal to negative Q of the surroundings. And why was that? If a system gives off energy, where's it absorbed? In the surroundings. It's the same amount, opposite algebraic sign, right? Right? Okay. So the Q of the surroundings, and remember we said we can use Q and the change in enthalpy interchangeably because we've assumed that pressure is constant. So we take the Q of our surroundings and we say that that's negative the delta H change for the system. Okay? All righty. And so now we can calculate the change in entropy for our surroundings. If we take this same chemical equation, we can calculate the delta H for the system, right? What did we do? We'd look up standard enthalpies, we'd calculate it, and we plug it in here. Now, we notice that we have kilojoules, and it wouldn't matter which way we did it. We could take our joules and convert them to kilojoules, but in this particular case, I took the kilojoules and converted them to joules, and then we divide by the Kelvin, all right? And so we end up with a change in entropy for our surroundings equal to 1,917 joules per Kelvin, okay? Everybody with me? Yes.
How did you know that Q was positive?
So it doesn't matter. Q could be negative, right? Okay, but if it is, then this is going to be positive. Okay, so we just, once we put in Q here, this had to be the opposite sign. Okay, just like I could write this as negative Q of the system is equal to Q of the surroundings. Right? It says the same thing. Yes?
Did you get the negative 571.7 kilojoules? Is that just, would that be from a table or would you?
Yes.
Okay.
So what I would do, now remember, enthalpy, delta H, how did we find the standard heats of formation? And for that particular case, we assumed that the elements were all 0, right?
Yeah.
And then what did we do? We make all the different